The closest star to our solar system is Proxima Centauri. It is roughly 40 trillion kilometers away. To cross that gap, the fastest thing in the universe, light, takes over 4 years. Using kilometers to measure something that far away is like using a millimeter ruler to find the distance between New York and Tokyo. It is simply the wrong scale. Even our own sun is 150 million kilometers away. To map our local solar system without dealing with billions of kilometers, astronomers use the astronomical unit, or AU. 1 AU is exactly the average distance between the Earth and the Sun. But once we look past our own planets, even astronomical units become too small. To measure the massive voids of interstellar space between different stars, we need a much larger tool, the light year. Navigating the cosmos means leaving human-scale rulers behind. We have to map the universe using the speed of light. The term light year creates a lot of confusion. Because it has the word year in it, it sounds like it should measure a duration of time. Think of it like saying, I live 10 minutes away. You are not talking about time. You are describing the physical ground you cover during that 10-minute drive. Light moves through a vacuum at exactly 300,000 kilometers per second. Letting that beam travel for 365 days straight covers exactly 1 light year, or 9.46 trillion kilometers. The gap between Earth and Proxima Centauri measures exactly 4.24 light years. We aren't measuring how long it takes to get there. We are using light as a physical yardstick to comprehend the sheer size of the cosmic map. When we look at that cosmic map from Earth, the sky is filled with glowing points. But not all of those points are the same. Stars are massive, self-sustaining cosmic engines that generate their own extreme heat and light. This visualization shows a process called nuclear fusion. Inside a star, intense gravity squeezes hydrogen atoms together so forcefully that they fuse into helium, releasing an explosive amount of energy in the process. Planets, dwarf planets, and moons are entirely different. They are solid rocks or swirling balls of gas that do not have the internal pressure to fuse atoms. They cannot generate their own visible light. This creates a visual illusion in the night sky. If you look up just after sunset, Venus appears to be one of the brightest objects visible from Earth. But Venus isn't burning its own fuel. It has a thick atmosphere of carbon dioxide and sulfuric acid that acts like a massive cosmic mirror, bouncing the sun's light directly back to our eyes. Separating the internal light generators from the passive light reflectors is the critical first step to accurately identifying what we are actually looking at in space. Historically, humans looked at these light sources and connected the dots. We call these patterns constellations, but they are actually 2D optical illusions formed purely from Earth's specific vantage point, not physically connected stellar neighborhoods. Astronomers use prominent groupings, like the 3 bright stars that make up Orion's belt, to quickly orient themselves and locate other, fainter objects in the broader sky. One specific star plays a highly specialized role. Polaris, commonly known as the North Star, exhibits a unique behavioral trait. It appears completely stationary while the rest of the night sky wheels around it. This stillness happens because Polaris lies almost exactly on the imaginary line extending from Earth's northern rotational axis. As our planet spins, that single point overhead stays fixed. Long before the invention of magnetic compasses, or GPS, ancient sailors and travelers leveraged this fixed celestial point as a reliable natural compass to navigate across open oceans and unmapped land. Constellations and star charts are highly practical mathematical tools that allowed early humans to map our own planet. Mapping the broader universe comes with a major complication. The cosmos is not a static grid. It is an actively expanding environment. Look at this grid. Think of it like drawing dots on a deflated balloon and then blowing it up. The galaxies, the dots, aren't physically flying through empty space away from each other. The physical space between the galaxies is stretching out. The hard evidence for this stretching space comes from a phenomenon called redshift. Redshift is a measurable change in the wavelength of light coming from distant galaxies. As light waves travel across this expanding void, the stretching of space physically elongates the waves themselves. By the time they hit Earth's telescopes, the light has been stretched toward the red, lower frequency end of the visual spectrum. Decoding this stretched light proves that we don't live in a fixed universe. We are sitting inside a dynamic, growing cosmos. Bringing our focus back down from the deep universe to our local solar system, that speed limit of light still dictates how we see our reality. Because the sun's light takes 8 minutes to reach us, we are always looking slightly into the past. Closer still is our nearest celestial neighbor, the moon. Its physical orbit around Earth dictates the monthly phases we see in the sky and exerts a gravitational pull that drives the tidal shifts in our oceans. We have also added our own objects into this local orbit. Artificial satellites are human-made technologies launched into space to look back at our planet and outward into the dark. These artificial satellites have a direct impact on our daily lives. They route the GPS navigation in our cars, beam telecommunications across continents, and monitor severe global weather patterns from above. All of this, the Earth, the Moon, the satellites, and our Sun, sits inside the Milky Way. This is our home galaxy, a truly massive, swirling, spiraling neighborhood of billions of stars, planets, and dust. The sheer scale of the universe is deeply humbling. But humanity's relentless drive to measure, to map, and to figure out exactly where we place within the cosmos makes us an active part of this extraordinary story.